I think for now, though, let's go ahead and get back on track here. The first thing that I did want to start with, of course, I think I showed this to some people have seen this already, but hopefully I realize the situation is more like gallows humor than anything else, but hopefully we can at least laugh at the picture just a little bit altogether. It is one of my favorite pictures of myself. I put this together during a staff meeting. I felt it was appropriate for the class at this one. So that's when you want to talk about artist renditions. This is kind of how I imagine the situation went. Nobody expected the steel chair. Nobody expected the steel chair. Yeah, there's a reason. That's my favorite picture of my face right there. Like, hands down. So, that aside, I didn't want to start a discussion on exam 2. Again, we'll talk about it a little bit more on Monday. I just, somebody was talking about the cruel humor of the physics department. I thought I would share, at least get a little bit of a laugh. Here we are on Friday. Sure. Yes. If you are happy with your first 2 exams, you are more than welcome to skip exam 3, right? It's no different than dropping the lowest exam or anything else. Yeah, that goes for anyone on that one. That's yeah. Only 2 out of the 3 exams will be counted, right? The lowest exam, regardless of if you had taken it or if you had not, whatever the score is on that one, the lowest one gets dropped. And when I say only 3 exams, I mean the 3 midterms. There is still a final, and that's a separate thing. The final is a cumulative exam, so that's why we don't necessarily group it in with the others. It's weighted just a little bit more heavily. It's a little bit longer of an exam, but and trust me, cumulative is in your favor, because by then you will be masters on a lot of these topics, and a lot of these questions will be much easier by then. And yeah, the final does not get dropped. It is not included. It is in its own little category off to the side. But anyways, going with the theme of our steel chair and everything else, right, and just getting knocked around by physics quite a bit, let's keep talking about these collisions. So last time, as we started to talk about these things, I might as well just jump into this slide right here, right? We talked about this brand new quantity called momentum, right? And this is essentially just another variable that can be used to discuss what's going on with the motion of an object. And this is finally where we're starting to look at the collisions, right? Up until now, every single time we had a collision, whether it was like the ball flies through the air and then it hits the floor, and like right there, I was like, stop. Don't go any further than that. Because as soon as that collision happens, it's a very different problem. If the 2 objects collide, very different problem. A lot of different things went into a lot of those situations. But now, with the language of momentum, we're finally able to start to take a look at what actually happens, going past that stop sign a little bit, going into what happens after the collision, what happens during the collision. And momentum is our key for that. So why is momentum so useful? Well, there's a couple different ways that we can use to talk about it, right? And we might even remember, as momentum is being introduced here, it's kind of similar to how we introduced force in the first place, if we remember that, right? We said, take acceleration, this thing that you already know and love, multiply it by a mass, and now you've got a brand new thing called force. Here, take velocity, something you already know and love, multiply a mass, now you've got a brand new thing called momentum. But this quantity momentum can be discussed in one of 2 different ways, right? First, we said if we're trying to change the momentum for any reason, if we need to change the momentum, then that is done by applying some force over some period of time. Right? And think, okay, so force can do a few different things. Forces are like our main bread and butter of motion. Right? Anytime we want to change the motion of any sort of object, we're generally using forces. And it's been a useful thing this entire time. For one, we saw that forces play a role in kinematics, we've also seen that if I take forces and I have them done over some distance, then I get work. So forces not only go into kinematics but they not only go into kinematics, they also go into energy. But now what we're seeing with impulse, they also go into change of momentum. Right? So whatever you're doing with forces, generally speaking, because forces are, things that are changing the motion of an object, we do expect forces to be essentially at the center of this big web when we're looking at how things move. Now, if I don't have any external forces, that is, if I have an isolated system, there are no external forces acting on my objects, then momentum is a conserved quantity just like energy was. Right? Think about when we were looking at conservation of energy, when we didn't have things like friction or an applied force or anything else like that. When it was only conservative forces, then we had energy conservation. In a kind of similar but not exactly sense, if we don't have external forces acting on our objects, on our system, so too will momentum be conserved. But so far, we have only seen circumstances where we have what are called perfectly inelastic collisions. And I'm going to get a little bit more into that, but perfectly inelastic collisions are the circumstances where two objects collide and they stick together, right? And they fuse into one object that then moves with that combined momentum. That is not the only type of collision, of course, but we specifically stated that in these inelastic collisions, energy is no longer a good friend to us. We can't use energy conservation, we have to use momentum. So let's look at another circumstance where momentum might be conserved, right? And that is explosions. Let's imagine, as we're sitting here talking about like bombshell in writing and everything else, let's imagine we've got some sort of bomb and it blows up into 3 separate pieces. Mass 1, mass 2, mass 3. Those 3 pieces, summed all up together, right? Mass 1 plus mass 2 plus mass 3 should equal the initial mass of this thing. But at the same time, there was no external forces acting on this thing in the first place. There's nothing going on that way. So what that means is that even though we have bursted apart into 3 pieces, and now we clearly see each of these does have a speed, that is to say, no kinetic energy to suddenly a lot of kinetic energy, energy conservation maybe is not a good friend here, but momentum is actually still conserved. When I sum up the momentum of each piece, I still should end up with the same momentum that I started with. And that's a really important point, right? Now let's imagine a slightly different scenario. Let's imagine that this thing was fired out of a cannon. So let's imagine that this thing started with some velocity Vx. Then what should the net momentum be of my 3 pieces? What do we think? mvx, exactly. The momentum that we end with should not be any different than the momentum that we started with. That doesn't necessarily mean that any of these have to change their direction. I might still have a piece flying off to the left. Right? If the entire thing was moving to the right, I can still have a piece going off to the left. That just means that the pieces going to the right are going even faster to the right. No, it is technically a version of, well, it's not quite a collision anymore, right? It's not a collision of an object. It is a circumstance where we would have a conservation of momentum, though. Because a collision is going to generally, it's kind of like the reverse of an inelastic collision. The inelastic collision is where 2 objects fuse together. They collide and they stick together. The explosion is the exact opposite. I have one object that splits into multiple pieces. So anytime I've got this object that splits into multiple pieces, it's very similar setup to our inelastic equations. It's just now essentially the sides have been reversed. So I want to try this out with a problem here. Let's imagine, and this is particularly apt because of the recent Mars mission, but let's imagine that you are in command of our next Mars NASA probe. It's a 2,000 kilogram probe, and it has been cruising at a casual speed of 25,000 kilometers per hour. It needs to slow down to a measly 15,000 kilometers per hour. And if it's going way too fast, then it's just going to burn up in the atmosphere, which is not actually a problem in the Martian atmosphere, but that's beside the point. If it's going too slow, then we're going to use too much fuel to actually try to get it down. So what we are trying to do is we are trying to get as close as possible to our sweet spot, 15,000 kilometers per hour. Slightly slower is better than slightly faster. But it's got a brand new braking system, something brand new that we're using, and it's using basic mechanics. We have these 5-kilogram pellets in the front of the satellite, in the front of the probe. What it's going to do is it's going to fire these pellets out at an incredible speed, 139,000 meters per second. And using conservation of momentum, this will slow the probe. So what I want you to do here, using this conservation of momentum, knowing what our final speed needs to be of the satellite, I want you to try and figure out how many masses do we have to shoot out of the satellite to get us down to the proper speed. I'm going to say the next probably 4 or so minutes, let's work on this one, and then let's come back together and see what we got. All right, let's start taking a look here. So, we need to draw this thing out first. And what better way to do this? Let's go ahead like this. We've got, essentially, let's draw our initial and our final pictures. Here's our satellite. Look at it. Beautiful, right? A marvel of engineering. It is initially traveling at some speed that I will call V0. Now, we know V0 is going to be our 25,000 kilometers per hour. And that is a lot of kilometers per hour. But I hate kilometers per hour, right? Because it's not a standard unit. I mean, it's in metric, so it's not the worst thing in the world, but I would much rather have this be converted into 6,944 meters per second. Much nicer. Now, so this is our initial picture. In the final picture, ideally, something has happened here where we are now moving at, let's call this a V final speed. Where V final speed is a measly 15,000 kilometers per hour. Again, not a very friendly unit, doesn't mesh very well with everything that I want to do, so I'm going to convert this immediately into 4,167 meters per second. Okay, but to do this, I have fired off some number of pellets forward. Right? Because what I'm trying to do is I'm trying to launch these things. It's kind of anybody that has seen any sort of sci-fi things where they're free-floating in space and they need to, I don't know, the situation where they have to push off or anything else like that, right? Conservation of momentum works here. What we're trying to do is we're trying to send things out forward really, really fast. We're trying to throw things that way so that conservation of momentum sends us the other way backwards. So we're not trying to necessarily turn ourselves around. We're still wanting to go in the same direction, but we want to slow it down a little bit. So we're going to apply the same idea, but just to slow ourselves down. So let's imagine we're firing off these kind of pellets, and each of these pellets has a mass, what I'll call m sub p, 5 kilograms, each of them moving at a speed v sub p. But what is that value? What do we think? What is v sub p? Does anybody have a number for that one? Any guesses? I would say not exactly. So the 139,000 meters per second is a start. But the 139,000 is not necessarily what the actual speed of these things are going to be, right? Because what these are is the speed relative to the satellite. That is to say, as the satellite is moving, when the satellite fires these things off, they're moving 139,000 meters per second relative to the satellite, if the satellite was recording that speed. So the actual speed is not just the 139,000, but it's 139,000 plus V0. if we're looking at it from Earth. Right? We're moving at these 25,000 kilometers per hour when we fire these things off, so they have the added speed of the 25,000 kilometers per hour. So, with all of that in mind, now we need to compare our momentums. My momentum when I start, what I'm going to do is I'm going to call this thing the mass total. And the mass of the satellite, the mass of the pellets, all that good stuff, right? So, let's say when we start, I would say that my momentum when I start is mass total times my initial velocity, right? Momentum, going in the right direction. And I mean specifically the right direction. I know that's left for you guys, so like that, I guess, when it gets reflected. I'm going to take the momentum of the satellite plus, let's say capital N, the number of pellets that we fire off, times the mass of the pellets, times the velocity of each pellet. Right? Because one of these is going to carry an m times v kind of momentum, so however many we fire off, that's how much momentum they're going to take with them. So I've got a question for everyone. What is the mass of the satellite? Do we know that number? I'm going to argue not 2,000 kilograms, but why? What's different? Yeah. The mass of the satellite, where did these pellets come from? They started inside of the satellite. The satellite fired these things off in the first place, right? The way we can imagine this is that I have, I don't know, say we didn't know how fast we were going to be going, so we stored all of these pellets in the front of the satellite, ready to be fired off. We're choosing how many of those we fire off. So if the total mass of the satellite was 2,000 in the first place, that is our M total. M total is equal to 2,000. But what we're looking at now, M sub s, the mass of the satellite after we have fired everything off, is whatever mass we started with, less everything that we have lost that we have fired out. So I'm going to rewrite this. The number of pellets that we have to fire. The mass of the satellite is whatever mass we started with minus however much mass we have lost to everything that we have fired off. Because this is, when we're talking about this 139,000 meters per second, that is relative to the satellite. That is, if the satellite was staying completely still, if we were testing this thing, let's say we're testing this thing on the surface of Earth, then this thing fires off around and it flies 139,000 meters per second forward from the satellite. But if the satellite's already moving, this kind of goes back into our reference frames. Right? When the satellite fires these things off, they are moving 139,000 meters per second relative to the satellite. But we're still already moving by nearly 7,000 meters per second. So this is essentially, if the balls were already moving at nearly 7,000 meters per second, and then we add that velocity to them, that's why we have this right here. They were already moving at V0, then after they have been fired, they have gained that additional 139,000. So with all of this in mind, we're after the number that we need to fire off, N, right? And at this point, I have all these other quantities. I'm ready to solve this thing out. I just need to do a little bit of algebra to remove some things. So first, I'm going to move the M total to the other side. That means this is going to become M total times V0 minus VF. I'm subtracting over my VF portion. On the other side, what I have left is the number of pellets times the mass of pellets, velocity of the pellets minus V final. With all of that stuff, I'm after N, divide by these other quantities. M total times V0 minus VF divided by mass of the pellet, Vp minus Vf. Slapped all together is equal to our number of pellets that we need. And when we do something like this, what we end up with is a number 7.84 pellets. But we can't fire off only a portion of the pellets. We don't have like some giant X-Acto knife to cut off only a piece and fire that off. So I'm going to go with Price is Right kind of rules here. Slightly under the value is a little bit better. Let's just go ahead and round that up. We need 8 pellets. So let's take a look at another one here. Let's try something else. Let's imagine, and here's a little bit of an interesting one. We're going to break this apart piece by piece. A ballistic spring system is used to measure the speed of bullets, right? So this will be a common theme. We'll see a few of these types of problems. A bullet of mass M is fired into a block of wood, mass capital M. They collide. Is energy conserved in this collision? What do we think? I would argue no. Think about what happens to that, right? There's a lot of heat that gets generated. The bullet has to like literally split the wood in front of it to actually embed itself in the wood. There's a lot of energy lost to that, I would think. And I would probably argue that most of physics would agree with me on that one. There's going to be a lot of energy lost in that collision. There's a lot of thermal energies, and breaking those bonds and splitting the wood and all of those details are places where mechanical energy is being lost. But it is a collision, and the two objects do stick together. But anyways, let's imagine, now once they have stuck together, right, this block-bullet combo has some velocity. It is sliding, and it runs into a spring. That spring is stuck to the wall. It's not going anywhere. And that block compresses the spring by some distance d. What is no friction in any spot? No friction over, it's a frictionless table, so there's no friction or anything, no energy lost that way. What is the bullet's speed in terms of these other 4 variables? So I want you guys to take the next, say, 4 or 5 minutes on this one, and then we're going to take a look together. Let's start taking a look here. So the first thing I want to do is I want to draw this out, and I'm going to draw this out in 3 phases. I think that's the best approach for this. So here's what I've got. Draw that a little bit more over. Phase 1. I've got here a block, right? Inspiring, amazing. I've got a bullet rapidly approaching this block. The bullet has a speed I'll call V sub B. It's got a mass, lowercase m. The block has a mass, uppercase M. This is what I will call step 1. Step 2. These two things have collided. Now, through this collision, right, the bullet is thoroughly embedded in the wooden block at this point. It's not going anywhere. These two things together now start to move. So here's the bullet inside of the block. This entire thing moves with a velocity that I will call V sub F. This is step 2. Step 3. This bullet block combo has run into a spring, pressed up against the wall, so it's not going anywhere, and it compresses said spring a distance d. And we will label that something like this. Let's say it started out there, something right there. That compression is a distance d. Call this step 3. So I want to analyze these things step by step. In my first picture right here, step 1 to step 2. Can we all agree? Of course, as it's going through this thing, the bullet is moving at such a speed, it is going to burn the wood. It is going to split a hole through the wood, right? There's not just, there's a gap left behind here. That gap required splitting of the wood, required breaking those chemical bonds. It would have a ton of friction with the sides of the wood, right? Because that's why it's embedded in here at this point. Not only because it has a bunch of stuff in the way of it that it's pushing past, but all the stuff on the side is still very tight around it. So I would argue here, energy is not conserved. Energy lost. Or at least mechanical energy is lost, right? Thermal energy, of course, all of that mechanical energy that we are losing is just going into thermal energy, but thermal energy is not energy that I want to talk about right now. So I'm going to call that energy lost. However, are there any external forces acting on these two? No, not really. I mean, maybe gravity's there, but I'm going to assume that this thing flies fast enough that gravity's probably not going to be a huge deal anyways. I'm going to argue for the most part that this thing has some sort of velocity that is relatively unaffected as it collides with the bullet. There's no big force acting on the both of these things at the same time necessarily, so I would argue that momentum is probably pretty well conserved. Now, I look at my second scenario. Step 2 to step 3. How much momentum do I have over here in step 3? What's moving? Is anything moving? Well, once the spring has been compressed, nothing. Right? When I've reached my maximum compression, that means the box has stopped. The spring isn't going anywhere. Right? And this is a little bit of a strange thing. This is something that I don't think we quite talked about when we talked about this in the first place, but where does the spring energy actually go? Well, what we're doing is we're essentially deforming some sort of object. We're deforming an object that's open to that. It's not just going to snap, but it would really like to go back to its original shape. So the spring is not moving. It's not like storing that kinetic energy as motion inside of the spring necessarily. Instead, we're slightly altering the atomic bonds inside of the spring, and those atomic bonds would really like to go back to how they were before. So I would argue that over here in step 3, there's no momentum. And if we had some momentum and we lost all of that momentum, I could maybe figure out how that impulse would be, but that sounds like a lot of work. I'm going to argue, though, that momentum is lost. And instead, I think about it like this. It's a frictionless table. It had a lot of kinetic energy when we started. All of that kinetic energy went into compressing this spring right here. That, to me, sounds like a conservation of energy problem. So I wanted to highlight these because these are my two possible conserved quantities, and I need to figure out if either of them are going to be conserved because that's going to help guide my solving process, right? My picture is now pretty well complete. I think I'm happy to start solving. So think about the variables that we have, the variables that we don't have. I am given two masses, the spring constant, and the total distance that the spring is compressed. We are asked to find what is that initial speed of the bullet. Okay, well, I see it right there, right? There's the speed of the bullet. So surely my relationship between step 1 and step 2 might help me find it. Let's try it. Let me take my momentum from step 1 and my momentum in step 2. My initial momentum looks something like this. That is the momentum of the bullet. Here is the momentum of the block. Right? Really pulling a lot of weight there. At the very end of the day, now I have the combined mass plus mass, and they're together moving at this velocity vf. So the final momentum should be this. Okay. V of b is what I'm really after here, but I don't actually know v of f. I don't have that quite yet. However, V of f not only has a relationship with step 1, but if I look over a little bit, well, it shows up in step 2. So maybe it relates to step 3 instead. And if we go along that description of energy conservation, then perhaps what I can imagine is that my initial energy is all kinetic. 1/2 mvf squared should be equal to, now at the very end of this, I have not changed my height. I don't have any kinetic energy left. All of the kinetic energy that I had has gone into spring energy. Kd squared. Now here, I look at this and I say, all right, I know K, I know D, I know mass. Whoops, I did mass wrong. What did I do wrong here? How should mass actually be? M plus M, exactly. It's not just lowercase m. Oh no, every single time. 1/2 m plus m. Vf squared. That looks a little bit better to me now. Now again, I know m, I know m, I know k, I know d. The only thing that I don't know is v of f, and that is exactly what I came here for in the first place. So, cross out the 1/2s. We don't need those. They show up on both sides. Divide over by the m. Take a square root. K d squared divided by m plus m. Now that we have Vf, we take that back. We look at my momentum equation, say I'm after V of B. Let's simplify this just a little bit before we start plugging things in. So this becomes V of B is equal to m plus m over lowercase m times V of f. Plug in V of f. And if you want to leave it just like this, I am happy with this expression right here. It depends only on the things that we actually know. So this is perfectly fine. If you'd like to simplify it just a little bit, though, we could write this out. I've got m plus m on top. I've got a square root of m on bottom. I've got a d squared inside of a radical. So I could do v of b is equal to, say, d over m. D over lowercase m times square root of k m plus m. This is just doing a little bit of algebra to simplify that up a little bit more. But I'd be perfectly happy with either one of these. All right. So, let's talk about a slightly different scenario. We have so far dealt with inelastic collisions, and specifically on that, we have dealt with perfectly inelastic collisions, or at least only the perfectly inelastic collisions when I'm talking about them by name. Realistically, there is another type of collision that's possible called the perfectly elastic collision. And an elastic collision is a collision in which energy is also conserved. So anytime I'm talking about inelastic collisions, that means that energy is not conserved, right? There are perfectly inelastic collisions, where a perfectly inelastic collision is where the two objects stick together as they move, as what we just saw in this last one, right? This is an example of a perfectly inelastic collision. But any collision in which momentum is not conserved, or rather, pull that back, momentum is conserved in collisions. Any collision in which energy is not conserved is an inelastic collision. It is just that there is a special type of inelastic collision where the objects also stick together. A perfectly elastic collision, on the other hand, has both energy and momentum conserved. And that means that we actually get some slightly unique equations for what happens when we're looking at the change of speed. So we have one special case here, where we have imagined that we have two objects, and object 2 has no velocity when it starts. Object 1 runs into object 2. If that is the case, then what we end up with here is this situation where we can find V1 and V2 in the final state based on essentially the relative masses of these two objects together. It's a certain special case, assuming that energy and momentum both be conserved. These are the equations that you get out. So I've got a question for everyone. Let's imagine a slightly different scenario. Let's imagine you were presented with a problem where you were given that I have, let's say, a red ball moving at 10 meters per second, running into a ball that is already moving at 5 meters per second. And you are told that this is still a perfectly elastic collision. Is all hope lost? Is there some way that we could possibly still use those brand new equations that we've got? What do we think? What would we have to do to what we see right here to still use our brand new equations? Any thoughts? How could we have it so that object 2 was at 0 meters per second? What about our good friend reference frames? Let's imagine for a second that we just revisualize this for a second. Let's imagine that we take this picture right here and we say, not quite. Let's imagine instead that this was completely stationary and this red ball was instead moving relative to the blue ball at a speed of 5 meters per second. But now, my reference frame kind of looks like this, where I'm moving, oh, that was supposed to be a line, but that's fine, that I'm moving 5 meters per second this way. Then I could solve out using these brand new equations. I could plug in all of my numbers as I would need to. I would find V1 final, I would find V2 final. Then I come back to my picture and I say, all right, well, now let's go back to where we were from before. Just add 5 to the right to both of those. Totally fine to do, right? Reference frames are a good friend for us in this case. So, of course, we could always just go through the derivation, right? It is not a big deal if we just say, all right, well, that's fine in its own right, but maybe I don't feel comfortable with those reference frames. Then all you need to do is you need to say, all right, well, whatever kinetic energy we start with should be the same as the kinetic energy that we end with. And using that condition and the fact that momentum should also be conserved, we can come up with any sort of equations we could possibly need, just in the exact same way. The methods lead us to the same spot at the end of the day. So I want to get a start with these two brand new equations, though. Let's give these things a shot. Let's imagine we are back at our shipping plant or whatever else where we're trying to move a bunch of things. A package with mass M is released from rest at a warehouse loading dock and slides down a 3-meter-high frictionless chute to a waiting truck. Unfortunately, the truck driver went on break without having removed the last box having a mass of 2M, 2 times the mass of the first box. Let's imagine, first case scenario, box 2 is a box of very active bees, and the box is covered in honey. When box 1 collides with it, that honey means they stick together and move together as one, a perfectly inelastic collision. In the second scenario, box 2 is actually filled with a bunch of rubber, and the 2 boxes go through a perfectly elastic collision and bounce apart. How high does box 1 rebound back up the chute? It's the same setup for both A and B, but the collision is very, very different. So what I want you to do is take the next 5 or so minutes to see if we can come up with good answers for each of these. And then we'll come back together and see what you got. All right, so let's start taking a look here. So I'm going to draw this thing in phases again. That's my big takeaway here. I want to draw this thing in 3 separate phases. Phase 3 is going to look a little bit weird, though. So let's start by just drawing this thing out. Let's do that first. So we say, okay, we've got something going on here where this box, it's got a mass M, it's sitting at some height h when it starts, and I'll just leave it as h. It's going to collide with another box down here. But let's even do this a little bit like this. Let's say box 2 down here is going to be, let me color this in gray, for example. So we see it's a little bit different. Box 2, these two collide together. This one's got 2m. This one's just got m. But what I'm going to do is I'm going to label this, this box right here has a velocity. Call it just v0 for now. That's fine. And I'm using v0 because I'm looking towards the future when I'm splitting this thing off in momentum, right? From the beginning here, I can see we start at rest. This is a bunch of gravitational potential energy. We slide down a frictionless curve all the way down to the bottom here. All of that gravitational potential energy is being converted into kinetic energy. Is there any momentum to conserve here in the first step? Probably not. It's one object. Right at the beginning here, it's not even like the block. The second block just doesn't matter until step 2. So for step 1 to step 2, this entire time that the block is falling, I'm not even going to consider momentum because there's not even a collision yet. There's no place for me to even think about conservation of momentum. Instead, here, it is an energy conservation kind of problem. Now, once I collide, here's where I'm going to kind of split off. Because let's imagine the first case that our box that we would see here, I've got my 1m box. We'll label it m. And in the first scenario, we said this is a box filled with bees, very active bees, and it's leaking honey. And of course, any label with bees has to be in all caps, but we said it's like leaking with honey the entire place. So the whole thing is sticky, and these two boxes are going to stick together. So I'm going to say that they're probably going to come with some V final stuck together. Here is my step 3. So let's try this, right? Let's say, all right, well, we're after this final velocity, right? That's the thing that we really want. My velocity coming into this, or rather my momentum coming into this in the first place, I would say, my initial momentum from step 2 was just m times v0. My final momentum, oh, and let me just go ahead and do that step again. Block 2, right, the 2m block was really not doing anything for me. It had no momentum when we started. But at the very end, these two boxes are now stuck together, so I have a total mass of 3m times whatever final velocity they've got together. That is, my final velocity here is just going to be, well, v0 over 3. The m's can cancel out, and I can just divide by those masses. I would say we're done, and it feels kind of like we are, but we don't actually know v0. So let's go back a step here real fast. Let's say, all right, well, v0 must come from step 1 to step 2, right? It's gravitational potential and kinetic. So let's just do that. We started at some height, mgh. We ended with a bunch of kinetic energy, 1/2 m v0 squared. v0 is just square root of 2 times g times h. And I'm writing it over here, and this is perfectly fine because this is the same setup for each of these, right? Whether it is a box filled with rubber and springs, or whether it is a box filled with honey and bees, the initial velocity of my smaller box as it's flying in here should be the same no matter what. So we can even just finish this up. V of f is square root of 2gh divided by 3. Perfectly happy with that one right there. So that was the scenario where we were going to stick together, right? This is our inelastic collision. Now, let's imagine the other scenario, right? What if it had been filled with rubber and springs? What if they bounced off of each other? Well, so hang on here. Let's back up for a minute. If we think back to that perfectly elastic collision picture, something sounds a little bit off here. Because this seems to imply that these two things run into each other, and then block 1 starts going backwards? That sounds a little bit strange. It had a forward momentum, so what's going on? Why is it like this? Let's imagine, what color is rubber? Is like a weird, slightly greenish color. Let's do it like that. This is going to have some velocity, call it V2 final. This would have some velocity, V1 final. This is how the problem kind of presents this, that it goes backwards, but we need to look back at the equation and figure out, is this actually something that can happen? So let's look at this picture. Surely V1 goes this way, right? That's no surprise there. That's what's going on. Based on what we see right here, based on what we see in this picture, how must M1 compare to M2? Which one's larger? M1 has to be larger. Exactly. Right, I know it doesn't look like it on the picture here, but let's look at what's going on in this equation. This is supposed to be the final velocity of M1. This is supposed to be this velocity right here. If this picture is trying to tell me that block 1 collides with block 2, or ball 2, and they both continue going to the right, this right here must be a positive quantity. M1 must be larger than M2, or else M1 would bounce back the other way. So if we reverse this scenario, if M2 is indeed larger, then okay, that makes a little bit more sense now. M2 starts going forward, but M1 gets sent back the other way. So when we look at our problem here, we see this 2M block is more massive. It's going to send my smaller block back the other way. Right? If you have ever played pool or billiards, if you're a very fancy person and like to use those kinds of names, right? Think about what happens when you first break when you're playing pool, right? When you start the game, you break everything. The cue ball comes in, it hits this big triangle of a bunch of other pool balls, and more than likely, it flies backwards. Because it's running into this really big mass, and the cue ball is comparatively the same size as the rest of these. So if it runs into all of the other ones, then it's going to send back the other way. On the other hand, if it's just hitting one ball at a time, then they'll both continue to go forward because, well, either the cue ball might actually stop, there might be some rolling friction. These are not technically perfectly elastic collisions. Perfectly elastic collisions you don't see very often, right? It's kind of like why we ignore friction and air resistance and everything else. For the most part, perfectly elastic collisions are few and far between. However, a lot of things get really close. And if they get close enough and the equations are easier than having to do the actual problem, let's go with the easy stuff and get most of the way there. But I wanted to bring up this example here because what we've got here is a perfect example of mass 2 is a little bit larger. That first object is going to kind of bounce back off. So we need those equations, right? That's what we're really after here. We need those equations. And in particular, I need specifically V1. Because I am asked to find how high does it go back up the slope? What is the y final on the slope? So let's try this. Oh, draw pad, please. Come on. The height, I think, was an initial 1 meter, is what we said. Was that it? I think it was just 1 meter. 3 meters. Just kidding. So, with these two things in mind, the equation that we really need, and I'm going to draw this in dark green to start. This is the equation that you'd pull directly off of the equation sheet. V final of block 1 is going to be M1 minus M2 divided by M1 plus M2 times the initial velocity of block 1. I don't really care about what happens to block 2. If I'm being completely honest, block 2 goes off, does what it does, whatever. I care a lot more about what happens to block 1 here. So, in this case, right, when we actually apply this to our problem here, V final one, I have mixed up the notation for this. I'll go with V1 final because that's what I wrote up here. Is going to be M minus 2M over M plus 2M times what I have already labeled as my V naught, what we had started with here. That is to say, this becomes negative M over 3M times V naught, or better yet, negative V naught over 3. And again, we feel clever. We're like, yep, we've got this. We're all set. But we need the final height, right? This thing rebounds back up. So I'm just going to take another energy conservation. This is kind of like a step 4 at this point by the time we're all done here. But we have bounced back. We've started to go back up, but this is just another energy conservation problem. We have kinetic energy. We're about to have gravitational potential energy. That is to say, mgy final is equal to 1/2 m v1f squared. I'll go ahead and solve out for this, right? We don't need these m's. We're looking for y of f. So this is going to become y of f is v1 final squared divided by 2 times g. That is to say, this becomes v naught squared over 18 times g. V naught, we know, is square root of 2gh, so this becomes 2gh over 18g. At the end of the day, y final, running out of space here, y final is just going to be h divided by 9. For total, if we want to, 0.33 meters. 18 is I've got my 2, and then I've got 3 squared on the bottom. Why doesn't the law of conservation of energy apply to sleeping in college? Because if you fall asleep, you have 0 energy, so when you wake up, you similarly have 0 energy. Sorry, that's just how it works. I don't make the rules on that one. Oh boy. I don't know what difference it makes. For some of those weeks and everything else, that's, I don't know what difference it ended up even making. That being said, if you study on, say, the 3rd floor of buildings, you've got more potential energy, right? That's a way that you could possibly get around this. But is there any other questions or anything else like that about all of this stuff? Are we feeling good? Is this going to be on the final? Of course it is. The constant question that I asked. The final is cumulative, so everything is going to be on the final. Okay, which part specifically here? Okay, so anytime we have a perfectly elastic collision, that is a circumstance where energy and momentum are both conserved. And we have essentially a special case already solved out for us. This is saying basically if you have the condition that kinetic energy initial is equal to kinetic energy final, and momentum initial is equal to momentum final, you end up with these 2 equations for the final velocities. We're just going to use this result to say, all right, well, we have this scenario right here where one block comes in, one block is at rest. When they collide, I have these expressions for my final speeds, or rather my final velocities. And I really don't care what happens to block 2. I'm only interested in what's happening to block 1, so that's why I have stolen this equation in particular. But it's... Yes, depending on which block it is, and only in the circumstance that we have a perfectly elastic collision. We are looking towards block 1 because we want to know how far up does the package M rebound. If we wanted to know what the final speed of block 2 was, then we would use the other equation. But since I'm interested in just what's going on with block 1, I'm only going to focus on the speed of block 1. Mm-hmm. All right, team. That's all I've got for the day. Thanks for being here. Thanks for sticking through it all. I, of course, always appreciate you guys showing up like this. It's always a pleasure to have you guys. If there are other questions or anything else, I am more than happy to continue chatting. If you've got some stuff going on, if you'd like to send me an email or anything like that, please do not hesitate to do so. But for now, I'll plan on seeing everyone again next time.